Alright, so here we have the first question from the topic of current electricity. The first one says a 12 volt battery is connected in series to a 24 watt lamp. So what is the unit of power? I'm going to write P here. Okay, so this is the value of P. A 12 volt battery, 12 volt is your voltage or potential difference or EMF. So I'm going to write V with it. The diagram shows the circuit. Okay, then the circuit is given. There are two resistors connect X and Y connected between the terminals A and B. They are connected with the 12 volt battery, and then you can see a filament lamp as well, or a light bulb. Anyway, the lamp is at normal brightness. Calculate the resistance of the lamp. Alright, so we are given with the value of P, the value of power, and we are given with the value of V. So one of the formula, the first and the foremost formula of resistance we get from here, V equals to I times R. And from there we can rearrange it into something like this. Resistance equals to the ratio of voltage to current. Now the thing is, we don't have the value of current here. Rather, we do have the value of power. Now there are different ways that you can do this question. One of the way is that you straight away apply the formula of electrical power. So we have three formulas. P equals to VI. Then we have P equals to I square R. Then you have another one, power equals to V square over R. Out of these three formulas, we think that the last one should be the most compatible one. The other ones can also be used, but then you'll need to find the missing thing. So we gotta use the last one. This would be the smartest pick. So power equals V square over R. You write it down like this. Now what is the value of P? 24 equals, what is the value of V? It was 6. So square of 6 divided by R, and that gives you R equals the square of 6, which is 36, divided by 24. Then you hit it on the calculator and let me know what do we get from here. Okay, then we have the next thing, determine the potential difference between the point A and B. And you see, this question is only of a single mark. So you should realize there won't be much of the mathematics here. So what we got to do is, let us take a look at the circuit, and we need to find the voltage across these points A and B. So this is kind of an easy one. So you see, the total voltage of the battery, or the EMF of the battery, is 12 volts. Out of that 12 volts, your filament lamp or your light bulb is consuming 6 volts. And the remaining voltage would be supplied or would be there across the terminals AB. So what you can do is 12 minus 6. Because out of this 12 volts, 6 volts is dissipated across the filament lamp. The remaining 6 volt would be across point A and B. And then you need to realize that the two resistors are connected in parallel with each other. So the voltage across both of them would be 6. So what we write here is that equals 12 minus 6, which is 6 volt. So you get 6 volt across the first resistor, you get 6 volt across the second resistor. Even if you had a third one here, you would have been getting 6 volt across the third one as well. Let us take a look at the next one. The combined resistance of the parallel pair of identical resistors X and Y. Okay, so what is the resistance of the single resistor? There are different ways you can solve this question. The easiest way is the voltage of the battery or the EMF of the battery was 12 volts, and the filament lamp was getting 6 volts, and the equal share, which is 6 volt, was given to the point A and B, cross the point A and B, and you get equal share of voltage only if the resistances are equal. So whatever the resistance of this thing is, which is 1.5 ohm, the same resistance would be across A and B. So the collective resistance across A and B of the two resistors would be 1.5 volt. Only then you can have equal distribution of the voltage, 0.5 ohm. Okay, and for the for your understanding, you can write here, because there is equal distribution of the voltage, that implies the resistances would also be equal. Okay, then we have the next thing, the resistance of X. Call it R1, the first one. This is R1, let's say, or Rx. This is R2. So we gotta find the value of R1. Now once again, you can do it different ways, and I'm going to choose the easiest way here. You see, the resistance of both of them, the collective resistance or the total resistance or the effective resistance, was 1.5 ohm. For the two resistors connected in parallel, the overall resistance is 1.5 ohm. What would have been the resistance of individual resistor? And since you know that these two resistors are identical, you see, resistance X and resistor Y, these are identical. So we know one thing. If you have two resistors, think about it. Two resistors are connected to a battery, let's say like this, and the two resistors are connected in parallel to each other. The resistance of the first one is 10 ohm. The resistance of the second one is also 10 ohm. Then I ask you a question. What is the total resistance of these two resistors once they are connected in parallel? The answer would be 5 ohm. Because the shortcut is, if the two resistors are connected in parallel and they have equal resistance, then the total resistance would be half of its value. Now here in the question, we're going the reverse way. We are provided with the total resistance, which is 1.5, but we need to find the individual resistance. So in this situation, what should have been the individual resistance? If you have 3 ohm here and 3 ohm here, only then the total resistance of these two resistors which are connected in parallel would be 1.5. There's no other way. So all you can do is, if you have two resistors connected in parallel and you need to find individual resistance, the resistance are identical, you need to find individual resistance, you divide the resistance by 2. And if you're doing the reverse way, you multiply the total resistance by 2. So you'll be getting the individual resistance. So the answer for this one would be 1.5 times 2, which would be 3 ohms. So this question number 2 is from the topic of magnetism and electromagnetism. Let me read the question. The diagram shows a horizontal wire PQ placed in a gap between north and a south pole of a magnet. there is a current in the wire in the direction P to Q. Okay, so you can say the current is flowing into the paper. Okay, taking a look at this, I mean they have tried to draw a 3D shape in which the current appears to be going into the page. So it is something like this for the current. A force acts on the conductor on the current carrying wire in the magnetic field. On the diagram, draw first one, an arrow, label them to show the direction of magnetic field in the gap between the poles of the magnet. So you need to draw an arrow to show the direction of magnetic field. If you have a north pole and a south pole, what is the direction of magnetic field?
North to south.
Okay, very good. North to south. Something like this. The next part, an arrow labeled F to show the direction of the force on the current carrying wire due to the magnetic field of the magnet. So you need to find the direction of the force on the wire due to a magnetic field of the magnet. Okay, so this one question is from the topic, or it has to be solved using we call that Fleming's left hand rule, which is used to find the direction of the force on current carrying conductor placed in magnetic field. The rule is called Fleming's left hand rule. What does the rule say? The rule says your forefinger or the index finger should be in the direction of magnetic field, which in this case your forefinger has to be towards the right side. Then it says your middle finger has to be in the direction of current, which in this case your middle finger would be inward. So I'm going to draw inward like this. And then you need to stretch your thumb as well. And once you stretch your thumb, the direction of your thumb, of your stretched thumb, would give you the direction of the force. So what do we get from here? Try to do it by yourself. So you see in the picture, first of all, I'm using my left hand, not my right hand. The direction of the forefinger or the index finger is towards the right side. My middle finger is inward and my thumb is then pointing downwards. Shouldn't that be the case?
Yes, sir.
Okay, so I mean, if we, for the first one, they asked us to just draw an arrow. So I'm going to draw a single arrow, and they asked us to label it as M. And for the second one, they asked us to draw an arrow and label it as F. So the force was downward, and then we have to label it as F. So this would be the direction of force, downwards. How? Using Fleming's left hand rule. Okay, let's take a look at the next one. State the effect of reversing the direction of current in wire PQ. Easiest question. State means no calculation, no explanation. You just need to state the fact here. If you reverse the direction of the current, the direction of force reverses. Okay, and then you gotta be careful with it. I've seen many students making a mistake. They'll be writing the direction of the force changes. It does change, but change can mean anything. For example, the direction of force is downward. Now the direction of force is towards the right side. That is also a change. If the direction of force is now to the left side, that is also a change. If the direction of force is, let's say, bottom left, that is also a change. But the thing that happens here is, if the direction of force was downward, this time the direction of force is going to be exactly the opposite, which is upward. So you gotta be careful with this. So number 3, the figure shows a transformer used to allow lamps of different voltage ratings to be operated from a 240 volts main supply. So you have different appliances of which are operated from the same 240 volt main supply. Alright, so all of those lamps would be needing different voltage. The primary and the secondary of the coil both have 500 uniformly wound turns. Electrical connections to the secondary coil can be made at 4 places. So that means although the secondary coil in total has 500 wires, but once you're making the connection using different wires, using different places, so you're changing the number of turns. For example, if you use the terminals XY, you're not using all 500 turns. You're using only this portion, these many turns, which might be 150. We don't know, but it would be less than 500. Anyway, let's take a look at the question. This is of 3 marks. The question reads, a lamp designed to light at normal brightness with a 120 volt supply lights normally when connected between W and X. Calculate the number of turns between W and X. So this is your secondary voltage, the voltage at the secondary side. The primary voltage was, as they have stated, 500 volts. The number of turns on the primary side is 500. Vs equals to 120 volts. Number of turns on the secondary side, which is the number of turns between W and X, needs to be calculated. This needs to be calculated. What formula do we have? The easiest formula from the transformers, you must be aware of it. The ratio of voltage, that is Vp over Vs, equals to the ratio of number of turns, Np over Ns. Let us insert the values that we have. We do have the value of Vp, which is 500. We do have the value of Vs, which is 120. We do have the value of Np, which is 500. But we don't have the value of Ns. That needs to be calculated. So that gives us, so I'm going to do bit mathematics here. 500 cancelled away with 500, then you'll be left with X equals to 120. Oh, sorry, my bad. The primary voltage was 240. Yeah, I've highlighted over there. Actually, the number of turns were 500, but the primary voltage was 240. Yeah. So the primary voltage is 240. Vp, that equals to 240. So what you can do now is you can cross multiply from here. For the students who find the ratios problematic, you can just cross multiply. This would be 240 times X equals to 500 times 120. From there you can find the value of X, hit it on the calculator, and let me know what do we get. For number of turns, we don't have any unit because it's a number. Okay, let's take a look at the next one, the lamp in A. What is the diagram A? Okay, no, this one, the part A. The lamp in A is connected between X and Y. So that means the voltage that the lamp is getting would be 120 volts, and it would be connected across the number of turns 250. Describe and explain what happens to the lamp. So between W and X, we were having 250 turns, and between X and Y, we would be having turns less than 250. As we can see from here, the number of turns between X and Y would be less than 250. Okay, this is what we can see from the diagram itself. Okay, so now we have the next one. State what would happen if the 120 volt lamp is connected between W and Z. Okay, so the lamp of 120 volt is connected between W and Z. So where's W and Z? So this is W and Z. W and Z. So what does that mean? Between W and Z, how many turns are being used out of 500? Think about it. Between W and Z, how many turns are being used? Than 250. Matter of fact, between W and Z means you're using entire coil as it is. So using 500 turns, right? So the thing is, the voltage across the lamp would be, in this situation, 240 volts, because once you had 500 turns on the primary, you were having 240 volts, and if you use the same number of turns on the secondary, you'll be getting the same voltage. So the lamp that was designed for 120 volts would now be getting 240 volts, and in consequence the lamp would be fused. So that's the reason you cannot place the lamp between W and Z, because if you place the lamp between W and Z, you're subjecting the lamp to full number of turns, which is 500, and in that case you'll be getting the whole voltage, which is 240 volts. Okay, question number 4. In the figure, XY is a copper rod placed between north and south pole of a magnet. Alright, so here you see the wire XY being placed between the poles and attached to a device, to an instrument. XY is connected to the terminals AB of a sensitive center zero instrument that measures current. You can write ammeter as well. So state the name of this instrument. The instrument that is used to measure the current is actually galvanometer. Sorry, is actually ammeter. But in this case, you can use galvanometer as well. It would detect the current, and in this situation, in this kind of experiment, we actually need to detect the current only, and that's it. We're not actually measuring how many amperes or how many milliamperes are there. Anyway, let's move on to the next one. When there is no current, the pointer on the instrument points halfway between A and B, which is the 0 mark. State what, if anything, is happening to the pointer when XY is held stationary. So in this case, nothing happens. To the next one, moved horizontally at a steady speed towards the North Pole. Moved horizontally at a steady speed to the North Pole. So you're moving this thing, XY is a wire. You're moving the wire at a steady speed towards the North Pole. So does that make any difference? No, because the number of magnetic field lines cutting the wire remains same. Whether you move it towards the left side, whether you move it towards the right side, same number of magnetic field lines would be passing through it. All right, on to the next part, part 3. Now you're moving the wire XY towards the right side. Once again, the number of magnetic field lines cutting the wire would remain same if you move it horizontally. You see, the thing is, the magnetic field is horizontal. It is from in this direction. So if the motion of the wire is horizontal, that is not going to make any difference in the number of magnetic field lines that change. So the rate of change of magnetic field lines would remain same whether you keep moving it. It would be the vertical motion that would change the number of magnetic field lines passing through the wire. The horizontal motion would not make any difference. So for this one as well, nothing happens. Move repeatedly up and down at right angle to the magnetic field. So you're moving it up and down, you're giving it a vertical motion. As it moves out of the field lines and into the field lines, there would be rate of change of magnetic flux linkage, and hence at one time when you're moving it inward or inside the magnetic field lines, pointer would move on one side to a positive side, and once you move it away, the rate of change of magnetic flux linkage is decreasing, the pointer would move on the negative side. Okay, so just one electrical device that makes use of this effect demonstrated in part B. Easiest of them all. This is the principle of the generator. So the motion is there. Okay, the movement to the wire, we are providing the movement to the wire, we are providing the mechanical energy, and as the output we are getting the current, we are getting the electrical energy as the output. So what device do we have? We call it generator.